This problem says, let R be an integral domain and consider the polynomial ring R join X. Suppose that A and B are elements of R, and A is a unit. Show that there is a unique ring automorphism of R touch X that is the identity on R and maps X to AX plus B. And then part B says, show that if phi is a ring automorphism of R join X that is the identity on R, then phi of X is equal to AX plus B. So in other words, phi sends the polynomial X to the polynomial AX plus B, where A and B are elements of the ring and A is a unit. Okay, so this problem is slightly confusing, but let's work it out. So it's helpful to be explicit about what this unique ring automorphism of R of X, R join X is going to do. So, um, let phi from the polynomial ring with coefficients in R to itself be defined by, so phi is going to send the polynomial f of x in R adjoint x to f of ax plus b. So it's going to send the polynomial f to the polynomial that you would get if you took f and you replaced all the x's with ax plus b. So you just plug in ax plus b for x. That's what this means. So uh, if you start with a constant polynomial, right, just an element of R, it doesn't have any x's. So when you replace all the x's by ax plus b, nothing happens. And so clearly then phi is the identity on R. And also, if you just start with the polynomial x, then you're going to replace every instance of x, so the one and only instance of x with ax plus b, and you will get ax plus b. So it also maps x to the polynomial x to the polynomial ax plus b. So that much is good. So we must show, what do we have to show? A lot of things. Phi is a ring homomorphism, that is that phi is bijective to show that it's a ring automorphism, and that it is the unique ring automorphism of R touch X that is the identity on X to X plus B. Okay, so um so let's note, um to check that it's a ring homomorphism, note that phi of f of x plus some other polynomial g of x, well, to add two polynomials is, f plus g be of that polynomial, their sum, which is f plus g. You take the sum polynomial and you plug in ax plus b for every instance of x, and that's the same as f of ax plus b to, uh, plus g of ax plus b. That's how polynomial addition works. And that is then phi of f of x plus phi of g of x. So that's the first property, and also phi of f of x times g of x. Well, that's phi of f times g of x, which by the definition of phi is the polynomial, the product polynomial, where you plug in ax plus b, which by what it means to be the product polynomial is f of ax plus b times g of ax plus b, which is phi of f times phi of g. Um, and then lastly, phi of 1 is definitely 1. We already said it was the identity on R. So phi is a ring homomorphism. Okay, so um, now let's show that phi is bijection. So suppose we'll start with injective. Phi of f of x is equal to phi of g of x. So what does that mean? That means f of ax plus b is equal to g of ax plus b. Now we have to be annoying and expand with coefficients. So we're going to let the ANs be the coefficients of f and the BNs be the coefficients of g. And so what this means is that AN ax plus b to the n plus AN minus 1 ax plus b to the n minus 1 plus dot 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 plus a1 ax plus b plus a0 is equal to bn ax plus b to the n plus bn minus 1 ax plus b to the n minus 1 plus b1 ax plus b plus b0, where a0 to an are the coefficients of f, and b0 to bn are the coefficients of g of x. Um, and f and g must have the same uh, degree for this to be true. So that's why we have n in both cases, because R is an integral domain. Um, so we can't get any, cancellation of things uh, killing the degrees prematurely. Okay, so now essentially by induction, we're going to see that the ANs have to be equal to the BNs. So, I mean, we'll just show that this implies that AN is equal to BN, and then a similar argument will show that AN minus 1 is equal to BN minus 1, and so on. Um, right, so uh, here we have to equate coefficients. And so let's look at what the coefficient of the highest power of x will be, right? So we have the highest power of x will be x to the n, and the coefficient on the left-hand side will be a and a to the n, and on the right-hand side will be bn a to the n from equating coefficients. Um, so an a to the n minus bn a to the n is equal to 0. So uh, an minus bn times a to the n, factoring out, is 0. And now, since a is a unit, hence not a zero divisor, units can never be zero divisors, and vice versa. Zero divisor, um, a to the n is not 0. And since R is an integral domain, uh, if a to the n is not 0, that means, but this product is 0, that means that an minus bn is equal to 0. So an is equal to bn. Right. Okay. So the highest degree coefficients of f and g have to be the same, and then you just repeat the same argument, equating coefficients down the line, and you see that all of their coefficients must be the same. Um, so I'll just say by induction, we're repeating the same argument, right? F is equal to g. Okay, so that proves that phi is injective. Um, Now let's show that it's surjective. So now let uh, g of x be in R attach x with c0 to cn its coefficients. Okay, so then let's look at where our map phi would send the polynomial g of a inverse. A is a unit, so it has an inverse. X minus BA inverse. Okay, well, that would be so um phi says that you are supposed to plug in AX plus B in for X. Uh, but G is first plugging in um or wait, first we're plugging in A inverse X minus B A inverse in for X. Um, so so let's look at G. G, right, so we start with G and then we have to plug in let's look at this polynomial, right? So we have C this will be Cn um, A inverse of AX plus B minus B A inverse to the N. Um, so we're starting with uh, well, this is just the first term, but um, we're taking um, G, which is, or we're taking G of AX minus A inverse X minus B A inverse, which is what you get when you start with the coefficients and you do, A inverse X minus B A inverse to the N. Um, right. Like we plug that in for X, but then phi says actually you replace your instance of X with X plus B. So instead of A inverse X, it's A inverse AX plus B minus that all to the N. Plus C N minus 1 A inverse AX plus B minus BA inverse the N minus 1 plus dot 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 plus C1 A inverse AX plus B plus BA inverse plus C0, which, okay, so now everything cancels and this becomes Cn x to the n plus Cn minus 1 x to the n minus 1 plus C1x plus C0, and that is just g of x. So we recovered what we uh, our polynomial g of x, and so uh, in particular, phi is surjective, right? So combined with what we showed previously, now we know that phi is a bijection and thus a ring automorphism. Okay, well, we're still not even done with part A. So now, suppose we have to show that it's the unique ring automorphism of R attach X that is the identity on R. Now suppose psi, that's the identity on R and maps X to X plus B, right? So now let's suppose psi is another ring automorphism uh, that is the identity on R and maps the polynomial X to the polynomial X plus B. Okay, well then psi of f of x is equal to, well, whatever the polynomial's coefficients are. So Cn x to the n plus Cn minus 1 x to the n minus 1, right? Uh, which is by the ring homomorphism properties, this will be the same as phi of Cn x to the n plus, phi of C1x plus phi of C0, right? And more ring homomorphism properties. That was the additive property. Now we'll do the multiplicative property, right? So we have that phi, that previous expression is equal to psi of Cn times psi of x to the n plus, and so on, and that's equal to, I'm not going to write the whole expression, it's equal to psi of Cn psi of x to the n, again using the homomorphism property. Okay, and now it's the identity on R, and Cn's are coefficients, so they're in R, so this is just Cn. And it maps x to ax plus b, so ax plus b to the n plus, okay, now I'll write one more term, right? C n minus 1, ax plus b to the n minus 1 plus and so on. And what is this? This is exactly what our original function phi would do to f of x, right? It would, phi says you replace all the instances of x with ax plus b. And so um, if we posit that psi is any other ring homomorphism, that is the identity on R and that maps x to ax plus b, then it's actually equal to phi. So phi is unique in the sense that we said. Okay. That completes part A. And now we move on to part B. So recall that part B said the following. Show that if phi is a ring automorphism of R touch X that is the identity on R, then it's going to send X, the polynomial X, to the polynomial AX plus B, where A and B are elements of R and A is a unit. Okay, so for part B, suppose B is a ring automorphism that is the identity on R. Okay, so let's examine where it's possible to send the polynomial x to. If it sent it to a polynomial that had degree strictly greater than 1, then by the homomorphism properties and the fact that R is an integral domain, then phi of any non-constant polynomial would have degree greater than 1 as well. And the constant polynomials already, right, because R is an integral domain, so we can't get any cancellation. And the additive property of and the homomorphism properties of phi would imply that phi of any non-constant polynomial has degree at least whatever phi of x is. And then the constant polynomials are already getting mapped to constant polynomials. So nothing would be getting mapped to polynomials of degree 1. Um, by the ring homomorphism properties and fact that R is an integral domain. Um, so phi wouldn't be surjective contradiction, or so phi wouldn't be surjective, right? So that means that um, therefore it must send x to some linear polynomial ax plus b, right, for some a and b and R. And now, well, it's a ring automorphism, so it's bijective, so it has an inverse, right? So we need to show that A is a unit, right? But let's consider the inverse. Well, then phi inverse of AX plus B would also be a ring homomorphism. So that would be phi inverse of AX plus phi inverse of B, and that would be phi inverse of A times phi inverse of X plus phi inverse of B. And since phi is the identity on R, then its inverse would also be, so this would just be A times phi inverse of X plus B. And the other thing is that this is phi inverse is the inverse, and phi is sending X to X plus B. So phi inverse is sending X plus B to X. So this is equal to X, right? Um, but now we don't know uh, where phi inverse might send X, but we do know that for this to be true, A would have to be a unit because whatever polynomial phi inverse sends X to, uh, when you multiply by A, you'll have to cancel the coefficient of X and get just one. So A must be a unit. And this finishes the problem.